We're going to continue our theme of what happens to reactions at equilibrium when we disturb that equilibrium and watch it restore itself to equilibrium. In this particular case, we're going to be looking at the effect of temperature or volume changes on a reaction that's at equilibrium and how it responds to that, and how we might predict the direction of its response. This material is all part of something called Le Chatelier's Principle, and here's a picture of Le Chatelier. And basically his principle says that whenever a system at equilibrium is disturbed, it will act to oppose the change that was acted upon it. Now, what does that really mean? Well, we've seen cases of that. For example, when we added a species, the response shifted away from that species. So if we added a reactant, we created more products. If we added a product, we created more reactants. The same would be true if we subtracted a species. So for example, if I'd subtracted a reactant, the reaction would respond by replacing that substance that was removed, so it would move toward reactants. If I removed products, the reaction would respond by replacing those products. So that's the sense in which Le Chatelier's principle works. Now, temperature changes are an interesting and subtle way that we can change the impact in a chemical reaction. I want to point out that endothermic reactions involve absorbing heat from the surroundings. We talked about that in Module 3. In order to gain the heat, then we end up with a higher enthalpy content in the products than we had in the reactants. That's what makes a reaction endothermic. For an exothermic reaction, on the other hand, it releases heat to the surroundings. So the classic example of an exothermic reaction is combustion, which releases a lot of heat and heats up its surroundings. Okay, let's look at endothermic reaction first. Since it is absorbing heat from the surroundings, in effect the heat is functioning as though it was a reactant with the other chemical reactants in this reaction. So by treating it this way, it helps us to use Le Chatelier's principle in a more intuitive manner, because if heat is a reactant, by adding reactants, we push things to products. Now let's see what that looks like on an energy diagram. So here is an energy diagram of an endothermic reaction. You can see that delta H is positive in this case. When we increase the temperature, it is pushing things back over that barrier into the products. So that's how it's aiding the reaction. So one way you can think of this is as we increase temperature, it's easier to get over that hill. So more stuff does. What about exothermic reactions? Well, now the heat is one of the products. So again, when we raise temperature, we're adding heat, so we're going to push things away from what we added. So in the case of our energy diagram, here's an example of an exothermic reaction, and now when we increase the temperature, we push things back over. I hope these pictures help you to develop your intuition for this, because it is a little subtle, but I think once you understand the pictures, then it becomes very easy. Another subtle change would be if we change the volume in a gas reaction. Now, the effect of changing the volume is basically to change all of the partial pressures in the volume. So what exactly does that mean? Well, if we decrease the volume, that means we're going to increase the pressure. Okay, think of it as decreasing the volume means squeezing down on the system. We're going to make it inhabit a smaller space, so we're increasing the pressure. So in order to follow Le Chatelier's principle, it means the reaction wants to counter this by trying to lower the pressure. But how can it do that? What can a reaction do to lower the pressure? Well, let's look at an example to illustrate how this might happen. Let's consider the reaction of sulfur trioxide into sulfur dioxide and oxygen. All right, this is a reaction probably takes place in the atmosphere. I know the reverse reaction certainly does. Now, as we look at all of the reactants here, I want to compare what's on the reactant side to what's on the product side in terms of what's in the gas phase. On the reactant side, I got 2 moles of gas over there, 2 moles of SO3 gas. On the product side, I've got 2 moles of SO2 gas and 1 mole of O2 gas, so I've got a total of 3 moles of gas. So the way this reaction can reduce the pressure, to lower the pressure and counter this disturbance on equilibrium, is to reduce the pressure by shifting to the left, by basically going to the side of the equation that has fewer moles in the gas phase. What would happen with this reaction? This is a reaction of HI, hydrogen iodide, to form hydrogen and iodine gases. What do you think will happen? Well, There's not going to be any shift because there's the same number of gas molecules on both sides of this equation. Each side has 2 moles of gas. So here's an event where we're not going to see any change by changing the volume, either increasing or decreasing the volume on this particular reaction. So if we were to do the opposite, if we were to increase the volume, that means the pressure would decrease and the reaction would counter by trying to raise the pressure. But that's really just the opposite of what I've been talking about. So hopefully you can figure that out on your own in other examples. So what is the summary of our system response? What is the summary of our Le Chatelier's principle? When we add material, the response is to reduce what is added. Okay? When we remove material, the response is to replenish what was subtracted. So if I add reactants, I'm going to reduce that by forming products. If I remove reactants, I'm going to replenish it by causing more of the products to go over toward reactants. If I increase the temperature, I'm going to shift to the side with higher enthalpy content. Notice in both cases, the shift was to the side that had a higher enthalpy, either the product or reactant, depending on which was endothermic or exothermic. When temperature is decreased, the opposite would happen. We didn't talk about this, but you can imagine that if temperature increases, it favors the higher enthalpy side. When temperatures decrease, it favors the lower enthalpy side. So it would shift to the low valley side of the chemical reaction. When volume is decreased, that increases the pressure, so it shifts to the side with fewer molecules in the gas phase. When volume is increased, it decreases the pressure, so it shifts to the side with more moles in the gas phase. I hope all this makes sense. You'll have some chance to practice this on a few sample problems in the lesson.